In the next video, we will talk about the stiffness and suspension component loads, more specifically centered in the McPherson and SLA suspensions. First of all, we will talk about the spring rate. The spring rate is the weight or force needed in order to deform a spring a certain distance. In the international system, we can measure the units by newtons per millimeter, or in the English system, pounds force per inch. This means that with a higher spring rate, it will take a stronger force to move the spring. So, what we were looking for is a low spring rate, which will make the spring move more and make the ride smoother. In the next slide, we can see all the calculations made to calculate the spring rate considering Hooke's law and radius of the coil. Next, we have the wheel rate, which is used to describe the spring effect at the wheel rather than the base of the spring. As we can see in figure 2, the bottom coil spring is mounted on the lower control arm about halfway toward the wheel from its inner pivot point. This causes two changes in relation to the spring. If the tire moves 2 inches, the spring will only deflect 1 inch, and if the load on the tire was 1,000 pounds, the spring would have to be able to support 2,000 pounds. The tire rate refers to the maximum speed a tire can travel during a certain period of time without failure. We can find this in every single tire. It's the last number, and it always has a letter as a nomenclature. We can find the nomenclature or the speed in the next table, going from M to Y, different speeds respectively. Finally, we have the ride rate. This is the effective stiffness of the suspension and tire springs in series, calculated by the next formula. Now that we know these terms, we can compare two different suspensions, in our cases McPherson and SLA. In the wheel rate, a coil spring for a McPherson strut is longer than a conventional coil. Comparing McPherson strut springs and SLA springs, you can find that McPherson strut springs are longer but narrower.